All right, good morning, everyone. Today we have a pleasure having, sorry, my computer is kind of working funny. Uh, we have a Kinleigh Fatheree presenting today. So Kinleigh is a completions manager at Seismos, where she supports operations in applying non-invasive real-time acoustic measurements to improve hydraulic fracturing execution and optimize stimulation. Her work focuses on using live subsurface measurements to evaluate perforation efficiency, cluster distribution, and treatment response during pumping. She previously worked in advanced fracture treatment design and on-site implementation across multiple North American basins and has provided direct technical support for refracturing, well rescues, and fracture diagnostic services. She holds a bachelor's degree in petroleum engineering from the University of Oklahoma. So, Kinleigh, please share your screen. The floor is yours. We'll be very happy to listen to your presentation.
Thank you so much for the introduction, and thank you for having me today. All right. So what I'm going to be talking about today is it's a combination of some publications that we recently put out, and they go nicely together. One of them is basically a production story that we co-authored with Diamondback. The other is a story about real-time closed loop execution. So what I'm trying to do with this presentation is tell this dual study of, first off, does perfect efficiency matter? Does it matter to your well performance? Second off, can you do anything about it? And is there anything you can do about it in real time? So can you use these real-time measurements to improve your completion decisions? So as an overview, we're trying to answer these two questions that you see here. Does what we're measuring predict production? Does it have any impact on production at all? And for that, we're using acoustic friction analysis, which I'm going to describe more in depth here in a second. And we're using the perf efficiency derived from acoustic friction analysis, or I'll just be calling it AFA after this, and seeing if that correlates back to 9-month production. So we're using this to validate this metric. And then we're showing that we can use it as an operational decision maker. So can we act on what we're measuring with intention? Is this perf efficiency measurement actually actionable? So all of this is connected through that AFA-based perforation efficiency, looking at production impact and productivity and completion quality overall, and again, seeing if there's anything that we can do to make it better. So does, perf efficiency matter? Of course, this is not a mystery to anybody, but just wanted to introduce this part a little bit because I think we think a lot about what goes on at the casing and not necessarily what happens just past it. But we've spent a lot of time as an industry dialing in perf diameters, phasing, total number of clusters, total number of shots, cluster spacing, really perfecting the limited entry methodology because we believe that distribution across your clusters has some impact to what's going on further on in your reservoir and then ultimately, how your well performs. So if your perforations are taking more of the fluid, you're going to have more fracture growth in those particular clusters and those perfs, and then less fracture growth in the ones that are taking less fluid. So ultimately, you're getting uneven fracture growth. Maybe you're bashing against other wells, which is something you don't want either. But ultimately, this is going to leave parts of your reservoir understimulated, and higher perforation efficiency basically tells you that more of your entry points that you've put in your casing are going to be contributing. So this is why we know that perf efficiency is that bridge between completion quality, and then productivity. And this is now what we're trying to prove. So really quick, just going into what we're measuring. Not going to spend a ton of time on this, but we want to establish a little confidence in the acoustic physics-based measurement itself. So AFA, like I said, is the method used in both of these studies, and the key output is post-sand perf efficiency. So really what we were trying to do with AFA is become this scalable method for getting some measurement of cluster distribution at scale, so across every single well across a program. And what we got out of it is this method that we're currently using. And the reason we were trying to do that is because we know that surface execution can look consistent from stage to stage if you're just looking at, treating pressure, rates, whatever is showing up on a screen in a frac van. But consistent delivery on surface doesn't necessarily guarantee uniform stimulation. Completion quality can still vary because near-wellbore conditions are changing. And from this traditional evaluation, you're often either getting this, after the stage is over, after the well is over, or even much later after the pad is over. So what we're trying to provide is a way that you can look at this during the stage. So while the stage is still being pumped, can we get this data without waiting a significant amount of time to get some sort of diagnostic back? So how AFA actually works, it's very simple, just to put that out there. Anytime a rapid rate change occurs during the stage, it's captured by high frequency pressure transducers. So that's really the main system component, is just the high frequency pressure data. It's what we're capturing this all from. Those transducers will be equipped on any well that's being measured. So we use these rate changes to create a controlled pressure transient. And when I say rate change, I say it means something small, 3 to 5 barrels a minute, and that can be a rate drop or a rate increase. Both of those are analyzable in the data. So those rate changes will induce a water hammer response that you can see over here, which we've all seen before. But what we do with this high pressure data is blow it up and piece apart a few different components. So these transients are telling us information. So this that you can see circled here is blown up to look like this. And this is literally exactly what our analysis process looks like. So what we're actually evaluating will look exactly like what you see on the bottom left here. So a few different components here. Section 1 is just the pressure change from the rate change itself. Section 2, we have our pipe friction component, and you'll get a slope here, and where that's coming from is the depressurization of the fluid column as that pressure transient moves up and down the well. Finally, we have the perf friction component, and that's coming from this inflection. So the restriction as the transient goes through the perfs essentially is where we get this impedance response and how we get perf friction. And then from there, we can determine total flow areas and things like that. So the most important thing to remember is that we're able to separate those pipe friction and perf friction components at measure points during the stage in a very simple way. And just visually what that looks like, there we go. So that rate change occurs. Each one of those points are measured as the stage progresses. So you can see rate change. We have our pipe friction component in that section 2, and then perf friction component. So from that perf friction, and what I'm for the most part going to be talking about in this study is as how we're getting total flow areas, how we determine entry hole diameters, and perf efficiency. So there's also an erosion model that's incorporated into this data, and we use that to get perf efficiency numbers. So that's all part of the process as well. But it all stems from that independent measurement of perf friction to get the rest of the data that we use in this study. So now that I've talked about what we've measured, now we're moving into, does this matter? The production study is telling us, does this perf efficiency data tie to early time oil production? This data really only matters if it ties to some sort of an outcome. So the goal is to not just measure efficiency, but to really show why operators should care. So the question that we posed was, does post-sand perf efficiency correlate with production? And this is a study that was done over a year or two, so pretty extensive. It was 85 Midland Basin wells that were filtered down. We used well average perf efficiency, and it was 9-month oil normalized by lateral length, since there was a variety of wells with different lateral lengths performed in this study. So just setting the stage a little bit here. And to talk about how this study was narrowed down and how we selected the 85 wells that we ultimately got to. So ultimately, we started with 200 wells that were monitored. We narrowed it down to 85 wells that actually had the post-sand perf efficiency data that we were looking for. And we filtered out anything that might have had some sort of unusual completion or something that was problematic with the well. Maybe there was an operational issue. Ended up filtering out some of those, and then we separated those into different geographic regions. So if the wells were, one-offs or one-off pads, those came out of the study. And then we also filtered it down to 4 primary formations that you can see listed here. So this makes our analysis a lot cleaner. The completion is less affected by unrelated well differences. Really gives us the opportunity to just focus on that one variable. It's, can be really difficult to just do well-to-well production comparisons. So we were trying to normalize for that as much as possible so we can see, really how is this post-sand perf efficiency data standing out. So I mentioned we gather this data on every single stage. The stage level perf efficiency had a wide distribution. Not surprising, these stages or these wells had quite a few stages. So overall, the stage count was quite high, and we, we know unfortunately that we can't get stage level production anyway. It would be very cool if we could. So we took that stage level data and averaged it just by well. So that reduces out that noise and really creates a production comparable metric. So this makes average well level post-sand perf efficiency the right input for this regression. Taking a look at the visual trend before we get into actual statistics. Overall, and this is filtered down to one of the specific areas that we were looking at, We did see that wells in those higher efficiency bins, so these are a well level perf efficiency binned into different post sand perf efficiency, and overall we see that the wells with the highest average post sand perf efficiency tend to have better 9-month production, tend to be better producers. The trend, of course, isn't perfectly smooth because production data is pretty noisy, and we use public production data for the study as well. So that was not provided by the operator. So all of this was available publicly. But in general, this relationship supports the idea that your completion quality does show up in production. And now we're going to talk about, does that relationship remain after we control for different variables? So just something important to touch on here. Again, I mentioned this was a regression model. So there's more statistical data in the paper. I'm just going to show this kind of at a high level right now. But we had quite a few model terms or variables in there. And the important takeaway is that anything or any p-value below 0.05 is considered statistically significant. So taking a look over here at the right, unsurprisingly, location stands out as being statistically significant. That, of course, makes a lot of sense. Bench also, of course, stands out as being significant. These really just lend credence to the model itself. But what we were trying to see really is, does anything that is actionable, and for this case, post and perf efficiency, is that statistically significant? So in this study, we of course see what that it is. So p-value of 0.03. So we can conclude that this measurement is contributing beyond just the location of the well, beyond just whatever bench it was drilled in. And really the big takeaway is down here at the bottom. We saw that a 10% increase in post sand perf efficiency led to, on average, an increase of 1,634 barrels per 1,000 feet at 9 months of production. So that in this data set is about a 10% production uplift. So you can just remember it as 10% equals 10%. And this is something that we've seen kind of in other areas as well, is that sort of 10% equals 10% number at 9 months. So, if you take away one thing from this part of this study, that this is definitely it. That we do see that post sand perf efficiency independently contributes, but also that we get an increase in production that is, that matters, is measurable when you increase post sand perf efficiency by that 10% number. So production relevance alone really isn't enough. It's great to have that information, but for optimization and specifically real-time optimization, we need the metric to respond to inputs or changes on the job. So as part of this project, SHAP analysis was performed. I'll spend a second describing it, but if I do a bad job, just please forgive me. The most important thing to take away is perf friction, or initial perf friction, stood out as having the highest perf efficiency impact. So if you take a look at the right over here, each one of these dots are representative of a stage. And the further away the dots are from the center line tells you how impactful it is to perf efficiency. Over on the right, it increases. Over on the left, it decreases. And then the color of the dot itself tells you what direction of the variable itself impacts perf efficiency. So for example, with perf friction, when perf friction increases, so that's what the red color is telling us, then you have higher post-sand perf efficiency. And then opposite with lower initial perf friction. So for example, you can see with average treating pressure, when you have decreased average treating pressure, you see higher perf efficiency. So that's just kind of telling you that if you have fewer perfs, your average treating pressure is going to be lower because you have better distribution. So a few controllable parameters really stand out here. Of course, perf friction really standing out as the most contributing. But takeaway here really is that perf efficiency is not just descriptive of a stage. It can guide us through our design choices, before the job even starts, and then your treatment choices as the stage is actually occurring. So that kind of wraps up the first half of this presentation, or the first study. We see the measurement is tied to production. Again, that 10% increase in perf efficiency for 10% increase in production. And we also see that we can actually act on what we're measuring. It's influenced by controllable design and treatment parameters. And this gives us the logic for real-time action. So if we see that perf efficiency can be changed, the next step is really acting on it during the stage. So here really is the pivot. We validated the measurement by saying, okay, we know that perf efficiency matters, it impacts production. And now with the next study, we're going to answer what can we actually do with this information? What does it look like? Can we provide useful data that's not just post-stage data? Because really the value is in this measurement being used while the stage is still being pumped. So moving into that closed loop study, so this talks about field implementation, operational uses, and how this measurement becomes an input to actual decision making. Talking a little bit about closed loop fracturing, I would say kind of a hot topic right now. Everyone has really their own version. I think what we do that sets it maybe apart a little bit was just really getting that downhole measurement that's guiding the closed loop workflow. So it's really simple. The components are just measure, calculate, evaluate, and then act, and then it really just repeats and repeats as the stage is progressing. And our version of measuring is capturing those rate drops during the stage. We calculate to get those pipe and perf friction components. From there, we use the perf friction data to get perf efficiency and UI. We'll compare it to thresholds that are set. And, this data looks different from basin to basin, well to well. So we'll make sure those thresholds are dialed in based on the information that we have about the area. And then from there, if needed, we act, or the system acts. And rate, viscosity, prop and schedule, or whatever options that you might have on the job is adjusted in order to create that intervention. So the loop is closed, as we say, when that measurement feeds the next decision that occurs. Showing the system level architecture here. These measurements can be directly integrated into frac control software. So any pumping company can use this data in their own software to form this closed loop workflow. And along with that, a decision tree logic, because it wouldn't make sense to just give measurements without providing some sort of information about what you do with it. So that's where the decision tree logic actually comes in. And these actions can be automated or they can be recommended to actual decision makers in a frac van, just kind of depending on operator preference. And then that continuous benchmarking is ultimately going to improve future wells and future pads. All goes into a database together. And the key here is that that measurement and the execution are very fundamentally related and linked to each other. So I just want to recall back to really how the measurement works a little bit so you visually can see what this will look like on a job. So this is, of course, actual real job data where these 4 rate changes were captured. And these are what we were making our assessments from. And all of these really serve a purpose. So from this initial measurement, we're getting a total flow area. So um, in most cases, in stages with good breakdown, we can achieve an initial perf efficiency of 100%, especially before sand starts hitting the perfs. So from there, we can get an idea of, what EHD actually is. Maybe perfs aren't exactly being shot exactly as expected. So it's really important that we get that very first initial data point in the very beginning of the stage. From there, we're taking a couple of assessments, and each of these mid-stage assessments are used to show if your efficiency is degrading. So is it just getting worse from point to point? And this last point here, that's where we're getting overall stage proficiency, but also uniformity index, which I haven't really talked too much about today, but just at a high level, we can use this perfs open data at every capture point during the stage and interpret that along with slurry volume in per open cluster to determine an overall UI once the stage is finished. So again, I didn't mention it too much in the study, but just in case you were curious about how we get that. So that gives us good just overall stage level data. And really, multiple measurements just matter because efficiency changes a lot during pumping. I really want to know, okay, did my proficiency drop to 50% because I never broke down my perfs to begin with? Or is, when I go to 1 pound during the stage, is that consistently what's making me lose perfs or something along those lines? It's just important to know that, if I lose half my perfs just at the very end of the stage, does that even really matter? So just capturing end of stage data really just isn't telling you the whole story. A little bit about the decision tree logic. So this is very customizable by operator, by area, which makes sense because I'm not necessarily going to make the same decision about a Bakken well versus a Niobrara well or whatever. The decision-making process is going to look a little bit different. And operators, they have different ways they like to do things. And sometimes you only have certain options that you can even use on a stage. Maybe you're rate limited to start with. Maybe under no circumstances can you increase your FR, things like that. So this is a collaborative process where we work together with the operator and the pumping company to come up with this together, basically. So this is an example, or this is actually the decision tree logic that was used in the results that I'm going to show you in a second. So at that first assessment point, if perf efficiency was greater than 75%, you would just continue on with the stage. And then, looking at the next assessment, you make the same decision. If it was less, the intervention here was to increase rate by a small amount. We do see a good relationship between flow velocity itself and getting better distribution, especially as perfs are being eroded. So in this case, we increased rate and to help prevent that efficiency decline. And then again, just kind of repeating the process every time an assessment was taken. Something that we kind of know is that you're basically going to start with your best perf efficiency at the very beginning of the stage. Once you lose a perf or lose a cluster, you're probably not going to get it back. So our goal here is not necessarily to increase perf efficiency once it gets to a certain point. It's really to arrest that decline as much as possible. So in this pad that I'm about to share, where the rate changes were performed, on average, we did start with overall good distribution, pretty normal to start with, very high perf efficiency. And then around that mid-stage evaluation point, we dropped to about 70%. And then here's where you see that divergence in stages with some sort of closed loop intervention. We had an overall average perf efficiency at the end of the stage of 60% versus stages with no intervention ending with 50%. So pretty, big difference there. Again, what we're trying to do here is just flatten out that curve a little bit, trying to prevent more perfs from being lost versus, trying to get up from the 70% point back up to 90%. So in this particular pad, the intervention that was performed, like I mentioned, was the small rate increase. And in this pad, that was an option. So we had some sort of design job rate, and we were able to increase and by just a few barrels. Honestly, it wasn't a significant rate increase, but just enough to increase that flow velocity through the perfs a little bit. But in these low performing stages or stages that needed some sort of intervention, we saw that it reduced efficiency decline by 52% on average for every stage. And we also saw a 4% uplift in UI, which, overall, we've talked so much about does distribution impact production? Obviously, now we see that it does. So even these small numbers can have a pretty big impact on what your overall well performance is. Looking at a different example of an intervention, and we always kind of get a lot of questions about this one. But the important thing to remember is, like I mentioned, the decisions themselves are very targeted to specific wells and specific areas. So for this particular well, for this operator, these were higher tortuosity. So they knew that targeted sand slugs can assist if they're starting to see some sort of distribution issue. So for this job, that was the intervention to just implement these sand slugs once they saw the decrease in perf efficiency, but again, specifically in these higher tortuosity wells. So the value of this closed loop system is choosing the right action for the measured behavior and then using the measurement to act on it using that action. I haven't talked too much about pipe friction, but there is a lot of value at getting pipe friction data at certain points during the stage. You know, water quality is constantly changing during a job. Your, you know, deliveries of different chemicals, who knows, maybe you get a bad tote or something like that. But that pipe friction data helps to identify FR delivery issues or water quality issues if there's a change during the job. Um, so any sort of impact on your FR performance is going to be identified. These insights really help with any chemical waste and operational variability. The way that I really like to look at it is you can also dial in that FR concentration pretty significantly. So we're, you know, for liquid FR, we're often just throwing 1 GPT or whatever down the well just because that's what we always do. But maybe we've maxed out our pipe friction reduction and we could save a little bit of money by doing a 0.87 or whatever GPTFR. And then ultimately, you know, save us a little bit of money on the surface side, which that's very, very immediately valuable. So, you know, really the biggest takeaway here is we have the subsurface simulation quality that we know it's important, but also this ties into surface execution, which really comes back to immediate dollars. In this study, we were able to evaluate 4 different pads. And all of this data comes back to a database. So every stage that we've measured really comes together to power learning. So that's over 100,000 stages at this point. Um, so here we saw, just with the baseline design, we started with an average perf efficiency of 55%, and then progressively increased from pad to pad. And finally, in our final pad, we saw a 22% increase in continued in perf efficiency through that continued optimization. So this really shows us the workflow is not just about a single intervention or a single stage here or there. It's really about that pad to pad learning and continuous improvement. So transitioning into some conclusions here, wrapping everything up a little bit, I just want to tie these 2 papers back together. This message again is really that validation, which was in the production study, the measurement, which we see that AFA proficiency is something that can be acted on with intention, either during the stage, between stages, depending on exactly what you're trying to modify. From there, we're acting on the data to form that closed loop intervention during the treatment itself. And really from there and what we're doing now is that overall improvement, that continuous benchmarking to strengthen future execution. So we can apply those learnings and really anytime you want, and make the next pad that you're about to do better as well. So ultimately, just really the key data points here. We see that a 10% increase in proficiency equals to about an additional 1,600 barrels per 1,000 foot at 9 months. Again, that catchy 10% equals 10% data point. So we know the measurement itself is valuable. We also see that those closed loop interventions reduced that overall efficiency decline by 52% on average. And from that pad 1 to pad 4, using sustained optimization, we saw an overall perf efficiency increase on average by 22%. So ultimately, AFA does provide a scalable, non-invasive way to link measurement to real-time optimization, which really comes back to well performance. So from this, we know perf efficiency. First off, it's measurable, but it's production linked, and really the most important takeaway is it's controllable and actionable. And that is what I have for you guys today. I would be happy to answer any questions.
All right. Thank you, Kinleigh. It's an excellent presentation. Actually, we have quite a few questions in the chat, so I'm gonna read them and then you will answer them. So we'll start with the first question by Greg Hadasevich. So did I hear it correctly that the study relies on the data collected by other parties? I'm interested in the data collection system, the sensors deployed, mechanism of data collection and transmission to the main uh, data server. Was it like Wi-Fi, Bluetooth, or fiber?
Got it. Okay. So how the data is collected. So break this apart. So on location, there is the high frequency pressure transducer per well. We have a data acquisition system that gathers frac data from the pumping service provider. So as far as what we actually put on location, that's it. It's the data acquisition box, some cables, and the pressure transducer. That's all sent to us just by Starlink. And that's all we need to do the analysis itself is just the pressure data, the rate data, um, concentration, just normal treatment job variables, but really the most important thing is pressure and rate. Um, and then that's all sent back to a real-time operating center. From there, I mean, that's all on surface. There's nothing going down hole. And from there, that's how we're getting the measurements. So the perf friction, pipe friction, perf efficiency is from the analysis of the pressure data along with the job variables.
Okay, yeah, makes sense. Thank you. So again, just to clarify, so basically, I mean, you have this data collected on location, and then over Starlink is being sent to the office, and then in the office, all the analysis has been done, and then for the closed loop thing, somebody calls from the office to the location and says, "Hey, now you need to adjust this," right?
So so that kind of depends. So they have a screen. Sorry. So the data in the closed loop workflow, they have a dashboard, which I didn't really show here. So they have a Seismos dashboard that shows you um, what my perf efficiency actually is. Unfortunately, I don't have an example in this presentation. Anyways, um, but I mean, yeah, essentially you get that perf efficiency pop up as a rate drop occurs. So if the closed loop workflow is being performed, you have that information, and either your frac system is set up to automatically make decisions based off of that, or if you have like a company man or consultant or whatever, they are making decisions off of the data that they see in in the dashboard. Or another example is some operators now have their own real-time operating centers where they have people who are communicating with the frac van, and they are also looking at the dashboard, and they are communicating to um, the who's ever on location to make the intervention. So honestly, there's a few different ways you can do it, but ultimately, in the closed loop workflow, everyone has access to the dashboard that's telling you what the measurement is at that moment.
Okay, thank you. Then we have quite a few questions from Ali. He already left, unfortunately. He has something else going on, but I'm gonna read them anyway, so you can answer for everybody. Um, if I heard correctly at the beginning, you indicated some wells were removed from the analysis due to some issues with completions. Just curious, did you try the model on them to see if they exhibited any relationship to production?
I It's not a great answer, but I don't. I would have to check. we do see it's important to sort of normalize by these things just because production data is so noisy. For the most part, most of the filtering was done just geographically. So we didn't necessarily want to compare wells that were super far from each other. So that's really where most of the filtering came from. If it was an operational issue, well, I don't think that there were that many of them, honestly, because you can really see here when you look at the geographical filtering, a lot of the wells came out just from that. So um, I can definitely check if they would like to reach out later, but I don't currently know the answer to that.
Okay. Next question is, I think you sort of answered this, but I think it's good to reiterate. So, like in your analysis of like which variables show the impact, you show that perforation diameter is at the top, right? But it's not an actionable one, right? So it's like your measurement, and so what is the case if you have larger hole, it's kind of large initial holes, just because you use kind of different perf gun?
Yeah, so the the way that we impact per friction in real time is that, of course, just rate. That's really the only thing that we can do in real time. But perf diameter, uh, just because I've talked quite a bit about real-time optimization and closed loop workflow, there's still a lot of value in stage-to-stage changes. So uh, what we often see operators do is play with their perf diameters from pad to pad or stage to stage, even if there's an option to switch out charges on whatever job you're currently on. So um, there's really so many different ways to use this data. And the stage to stage is just as valuable as the real time. So if uh, if somebody is looking to just really optimize what charge they're using and what diameter they're shooting, then definitely, yeah, the stage to stage optimization is just as valuable to that perf efficiency component.
All right, and then the last question from Ali again is just to clarify it. So, are you able to capture each perforation diameter within a cluster, or you kind of have the average measurement for any given cluster?
We capture the average diameter of the perfs that are open. So, no, we can't see individual perfs, but we can get that average number from a total flow area.
Okay, thank you. And then we also have a question from Mark Pearson. Mark, I think it would be best if you can just ask it, if you just unmute yourself and actually ask this question, because it looks quite kind of alluded. Mark?
Okay, sure. Can you hear me?
Yes.
Okay. Yeah, hey, great presentation, Kinleigh. On that plot that we were just looking at in on initial perf friction is the largest determinant of post-sand efficiency. Um, what is the quantum? What is the magnitude where you see a positive and a negative? Is it 1,000 psi? Is it 1,500 psi? Is it higher?
Um, I know the answer to this question, or I know the question to this answer exists, and it's in the paper.
Okay.
And I don't have it off the top of my head. Um,
So I got to go read the paper, is what you're telling me. Okay.
it's a really good paper, and I'm happy to send it to you after this as well.
Please,
Um,
please, please oh,
yeah,
I'm sure I have it, but go ahead and please send it to me. Okay.
yeah, definitely. I'm happy to do
Okay.
that.
Thanks a lot.
All right, so I think we are out of questions in the chat. So maybe anybody else from the audience have any last minute burning question? While everybody's quiet, actually, I have one. So since we have some time, I'll ask you, Kinley. So, it looks like, this technology has been, maturing over the last few years, right? So it's not new, but I'm just curious, where do you see where is it going? It's like, what's the future? It's the goal kind of just to collect more and more data, or you kind of, every month, every year, you are improving on the quality of your measurements, so you keep adding measurements. So where is all this going? Basically, that's my question.
Yeah. There's honestly a few things. Yes, we are constantly improving the measurement. We're part of the peer consortium. So I mentioned this erosion model, that's part of it. We're always trying to improve on that because that's really one of the biggest unknowns when we provide perf efficiency is, do we exactly know how perfs are eroding as profit goes through it? So that's, yes, continuous improvement for sure, always part of it. And like maybe it seems a little bit cliche to say, yes, we want every stage to be, excellent. We don't want a single stage where there's a problem. Yes, that's what the real-time optimization for, but there's really also a quality control component to this. There's sometimes a lot of mystery into what goes downhole, and being able to say, I know exactly what my FR is doing, or I know exactly how my perfs are being shot. I know that my plugs are holding, or that, there's no issues with my casing. It's just a really easy, simple to use check. And these are things that we're catching. Didn't have time to talk about this here, but for sure, plug stability. We're putting out a big um, plug integrity study here soon to kind of show plugs are failing a lot more than we think they are. And we're also, catching casing issues before there are major problems that you can actually see because, wireline had a problem or something like that. So that's really a big part of this as well, is that QC component. But yeah, I would say those are the main things.
Fantastic. Thank you so much. Well, any last minute burning questions from the audience? Just unmute yourself if you want to ask a question. It's count of 3, 2, 1. Well, no more questions. In this case, I would like to thank you, Kinleigh, so much for your presentation. It was super, super informative. So yeah, until next time.